Okay, so let's do a perhaps more standard example for the normal distribution to be used in an application in which we're going to look at the normal approximation to the binomial distribution. Okay, so we'll come to the binomial distribution in a moment, but let's think for a moment about n random variables which are not binomial, but they're Bernoulli trials, what we call Bernoulli trials. So these random variables, each x can take two possible outcomes. We have the value 1 and the value 0. They're binary random variables. And the probability x equals 1 is p, and the probability x equals 0 is 1 minus p. And we're going to keep it non-degenerate, so we're going to insist that p is strictly between 0 and 1, so we're not guaranteed to get one of these each time. So probability x equals 1 is p, probability x equals 0 is 1 minus p. And we're going to consider the sum of n such random variables. So S is the sum of xi, I equals 1 to n. So we've got this summation notation where we substitute I equals 1, I equals 2, and so on in the sum and add them all up. And that's exactly the same as n times the mean. Okay, the mean would divide by n, so if we add them all up, it's the same as multiplying by n for the sample mean. And so the sum of n Bernoulli trials is the new random variable we're going to consider. And by the central limit theorem, we know that for large values of n, the sample mean, x bar, is approximately normal. And so that should tell us something about S. Okay, so S itself will also be normal because that's just a constant times another random variable which is normal. And in particular, the mean value for S, we'll call it mu. The mean mu is S, which is n times the expected value of x bar. And the expected value of x bar we know is the expected value of x. That's n times the expected value of x. And the variance is going to be n squared times the variance of x bar. And that's n squared times the variance of x over n. And that's n times the variance of x. So we have the distribution of S is normal with a given mean and variance. And then, of course, we can see how that relates back to the binomial. So S we can recognize as the number of successes in n trials. So we have these Bernoulli trials. Each trial has a success or fail, 0, 1 possible outcome. And S just adds up or counts how many successes there are. So every time we have a success, it's a 1. And so we count by adding up x's, we're essentially counting how many successes in n trials, and the probability of success in each trial is p, and so we would say S has a binomial distribution. Okay, so by the central limit theorem, we're saying that S is normally distributed with a mean n times expected value of x, and variance of S is n times the variance of x. And for these very simple Bernoulli trials, we could compute the expected value of x, which is 1 times the probability x is 1, which is p. So 1 times p plus 0 times 1 minus p would give us the value p. The expected value of x squared is 1 squared times the probability x equals 1, which is 1, and 0 squared times the probability x is 0, which is going to be 0, and so we add those up. We get the value p, the expected value of x squared. And so the variance of x, which is expected value of x squared, minus the mean squared, is just p minus p squared. So that's the value p times 1 minus p. So we can now substitute the variance of x and the expected value of x into the parameters for the normal distribution, the mean and the variance. And we arrive at the result. It says as n goes to infinity, the quantity S, which has got a binomial distribution, converges to a distribution which is normal with mean np and variance np times 1 minus p, or sometimes written npq in the case that q is 1 minus p. Okay, so this is, if you like, an application of the central limit theorem that says although it applies to means, we can actually apply it to sums. And in particular, it means we can approximate the binomial distribution with a normal distribution. And if you think about the binomial, it is relatively cumbersome to compute all the probabilities and to add them all up. And the normal distribution gives a very fast way of approximating them for large values of n. Okay, but before we do the approximation, I'm going to just mention briefly something called the continuity correction. And the continuity correction actually makes the approximation that little bit better. And it works like this. So S, which is binomial, can take values 0, 1, 2, up to n. It's a discrete random variable. It can't take the value 2.5, it can't take the value root 2, it can't take the value pi or whatever. All these values in between, it misses off. Whereas the normal distribution is a continuous random variable. And so we make some adjustments to try and make a better approximation. So in particular, we can notice that for a discrete random variable, the probability of being less than or equal to a value is not the same as the probability of being strictly less than a value in general. And if we're going to make this approximation, where we approximate a discrete random variable by a continuous random variable, then we use a continuity correction. And I'm just going to state the formula here for what you do. So if S is binomial with parameters n and p, that's a shorthand way of saying S is the number of successes in n trials with the probability success in each trial is equal to p, then to calculate the probability S is equal to r, where r is an integer, we can note that's equal to the probability that S lies between r minus a half and r plus a half, because there's only one value in there that S can take anyway. And then that's approximately equal to the probability that the random variable x, which is normally distributed, lies in that same range, where the mean and the variance of the normal, np times 1 minus p, are the same as the mean and the variance for S. Okay, so this formula, of course, wouldn't apply at the end values. So when r equals 0, we wouldn't do 0 minus a half for the normal. We'd just go to infinity, minus infinity. And similarly, when r equals n, we wouldn't go just to n plus a half. We'd go up to infinity. So the probabilities then would totally add to 1. But for all the values in between, from 1 to n, we have this approximation. And of course, we can use that also in the case where we want to find the probability of outcomes up to a certain point. So for example, the probability S less than or equal to r, we'd approximate by the probability of x being less than or equal to r plus a half, because we want to include r, and that means we extend up to r plus a half for the normal. And another example, probability of S being strictly greater than r, we look at the probability of x being greater than or equal to r plus a half, and so on. So you can see then the idea behind the continuity correction of including or excluding a particular value means you either add or subtract a half as appropriate. Okay, so let's just do a few comparisons to see how well the normal approximation or the normal distribution approximates to the binomial. And for various values of n and p, we're going to compare the probabilities for the binomial distribution, taking a value r, with probabilities obtained using the normal approximation. So the normal approximation are the red bullet points, and the binomial probabilities are obtained with the sort of plus symbols. So on the left-hand curve here, we've got the case where there are n equals 10 values, and the probability of success in each case is a half. Okay, so this is the situation we'd have if we tossed a coin 10 times and we count how many heads there are. Then we're computing the probability of 0 heads, 1 head, 2 heads, up to 10 heads. And so for each of these, we've got a probability obtained by the binomial And then to compare with that, we've got the red marks showing what would we get if we used the normal approximation for computing those same probabilities. And that left-hand graph actually looks pretty good. Even with n equals 10, we've got quite a good approximation for the normal to the binomial. The middle picture, what we've done here is to move p down to 0.2. And you can see if we have smaller values of p, then we're going to get fewer successes. And so it's kind of scrunched down to the left-hand side. We have higher probability on the lower counts. And you can notice in this case that the approximation is not so good. Okay? We've got quite a bit of discrepancy between the binomial and the normal. And we probably wouldn't be happy with that for an approximation purpose. And on the right-hand side, we've got a larger value of n equals 50, and p equals 0.4. And here again, we can see really very good approximations right across the whole range. A few bits in the middle are not quite so good, but they're really, overall, it's a very good approximation. So you can see that the success of the approximation depends on, in this case, the value of n and the value of p. Okay, n equals 10, p equals a half was okay, n equals 10, p equals 0.2 was not okay, n equals 50, p equals 0.4, it looks okay here. Okay, so one of the questions then is how large a value do we need n to be before we get a good approximation? And it all depends, as we've seen in the pictures, really on what the distribution of the underlying random variable is. So remember, we don't need normally distributed random variables, and how large n has to be before the approximation is good will depend on where we're starting from. So some rules of thumb. First of all, if x is normally distributed, then the result holds exactly for any value of n. Okay, clearly n equals 1, the sample mean, or x bar is just x, and it's already normal, and it holds, in fact, for any value of n in the case that x is normal itself. The second case is to say if x is symmetric and unimodal, that is to say you have increasing probabilities in the middle, decreasing on either side, and some sort of symmetry to it, as it was for the binomial, then you can get pretty good approximations for n as small as 10. Not too bad. Obviously, it can be better. If you have a distribution which is quite skewed, as it was for the case when p equals 0.2, in that case, you might need n to be at least 30. So round about 30 could be enough in those cases. And if it's severely skewed, maybe if you had p down to maybe 0.1 or 0.01, then you would need n to be about 50 or more. But it clearly depends on the value. But for sort of normal sample sizes that we tend to get in today's data sets, n equals 30, n equals 50 is usually attainable. And so we can be fairly confident in those situations that the distribution of the sample mean is going to be approximately normal. But in general, of course, it depends on the circumstance and what you're going to use it for at the end, how close the approximation has to be. Okay, so the central limit theorem is very clear to state, and it's very short, quite messy to prove, quite easy to illustrate, but why does it matter? Why is it important? And this last bit here is perhaps the most important. It shows why the central limit theorem is the most important, or one of the most important theorems in statistics. So first of all, we've already seen it can be used as an approximation. Okay, it works as an approximation for the binomial and for other distributions as well. And in that context, it's a valuable thing to have, although with computers nowadays, that's not so important. You can usually compute the probabilities well enough and quick enough with a computer without reverting to the normal. The most useful thing is that the central limit theorem enables what we call statistical inference. Okay, it's a slightly odd word, this inference, slightly odd usage. And I've got a kind of working definition here. So statistical inference is a probabilistic statement made about the population on the basis of information contained in the sample. So what we're saying is, an example of this would say, we've taken a random sample, perhaps an opinion poll or something like that, of how people are going to vote in the election. And we're saying on the basis of the sample that we have, maybe 1,000 people, we're going to make a prediction for the population as a whole. Population as a whole, of course, we haven't asked questions of the population as a whole, but we're making a statement about the population as a whole. We're predicting, for example, that a certain party is going to win the election based on our sample. That's an example of statistical inference, which says we're making a statement about the population on the basis of the sample. And it's not just a statement saying we think the party X is going to win. We could make a more precise statement with an associated probability of that outcome, or the sorts of outcomes we might get. And in particular in statistics, with the central limit theorem, we can form confidence intervals. So we can say, because we've observed this sample, and we've computed this sample mean, it gives us a statement or a confidence that in the population mean is within certain bounds related to the sample mean that we've already calculated. And related to confidence intervals, we could also carry out hypothesis tests. So, for example, is it reasonable to say that this new drug is actually no better than the old drug? Is there evidence in the sample to say this new drug is better and it should go onto the market? Or is there no evidence in the sample and we should just discard the new drug and not bring it out to development? So the two concepts of confidence intervals and hypothesis tests are key things which are used in science to further understanding, to bring new ideas and new theories, really as a result of statistical inference, which is possible because of the central limit theorem.